Thus far, we have been learning about one-sample tests. These are tests where we draw a sample from a population. Now, when we learned about those tests, I told you that anytime you draw a sample from a population, that what is true of that population should be true of the sample drawn from that population. In other words, the mean of the sample should be the same as the mean of the population. And it works the other way. So if we know something about a sample, we can extrapolate from that back to the population, because what's true of that sample should be true of the population from which it was drawn. Great. But that's one sample from a population. Many times, we want to compare two samples. We want to compare one sample to the other. And this can create a little bit of a problem because we know that anytime you draw a sample from a population, there's going to be some slight differences between the sample mean and the population mean. And if you draw two samples, there's going to be some slight differences between those two means as well. What we need is a way to evaluate whether these differences that we find really matter. So to illustrate this, I want to watch a movie. Now, I wish we could pick from really great movies, but unfortunately, the only two that I could manage to pry out of this abandoned red box near the Walgreens were these two. The Fast and the Furious, Tokyo Drift, and Too Fast, Too Furious. The ratings for Tokyo Drift, 37% versus Too Fast, Too Furious, 36%. So we have 37% compared to 36%. And here's what I know about numbers. 37 is more than 36. So clearly, Tokyo Drift is the better movie. It has a higher rating. Is 37% really all that different than 36%? Is it enough to say that it is truly different in a way that matters? Well, that's the kind of question that we're going to be answering using a proportion test. I have two samples, two movies. I need a way to compare the proportions within these two movies. I'm going to teach you about two different forms of a test. They're both going to use a z-statistic, which means that they're both reliant on the normal distribution. In fact, that's why I put these two tests together. Because they both rely on the normal distribution, they'll have the same way of calculating a critical value. The first of the tests I'm going to teach you is called a two-sample z-test. This uses means. I draw one sample from a population, and I calculate a mean of that sample. And then I draw a second sample from a second population and calculate the mean of that sample. I want to know, are those two means statistically significantly different? I'm going to start with an assumption that they are not different, that they are in fact the same, that mu1 equals mu2. And then I'm going to do a test to figure out whether the evidence supports that null hypothesis assumption. Of course, there's other ways of looking for differences between groups, not just means. I could look for proportions, like the proportion of 37% versus 36% we saw with those two movies. If I have a percentage or a proportion, I can do a two-sample proportion test. Again, I'm drawing a sample from a population. I'm drawing a second sample from a population. My assumption is the proportions of those two populations should be the same. That's my starting point. That's my null hypothesis. And then I'm going to test to see whether there is sufficient evidence to support that null hypothesis. We're going to do the two-sample z-test first, and then we're going to look at a proportion test. And again, both of these rely on that normal distribution, which makes it very similar in the way we calculate our statistics. A two-sample z-test is a parametric procedure. What does that mean? We're drawing a sample from a population. The mean of a sample is a statistic. But the mean of a population, that's a parameter. So anytime we're using a sample to make an inference about a population, we're doing parametric statistics. So parametric statistics involve drawing from a population, learning something about a sample, and then extrapolating back to that population from which the sample was drawn. So in our two-sample z-test, we're going to compare whether one mean is statistically significantly different than another sample mean when the standard deviation of the population is known. So I have one sample drawn from a population, it has a mean. I have a second sample drawn from a population, it also has a mean. But I know something very specific in this example that I typically don't know in any of the other tests that we're going to learn about, and that is I know the standard deviation of the population. How do I know that? Well, probably because it's given to me in the word problem. But the way that I would maybe calculate that is if I have a lot of information going back several years, I have good historical data where I can actually calculate it, or I know something from other research. There's something that gives me access to a population value. So in our examples, I'm going to be using historical data where we calculate some value and then that will stand in for our population value. So I've got to tell you, this is actually a very rare test. It's very rare that we use this test because we usually don't have those population values. Usually what we're going to do is take a sample from a population and then we'll take the standard deviation of that sample and use that to estimate the standard deviation of the population. But that creates a little bit of a problem. We have to account for that degree of freedom that we're losing. So we're going to use a different type of distribution. We're going to use a t-distribution instead of a normal distribution. We're going to learn about t-tests next week. So for this week, we're going to be using a normal distribution based on some information that we typically wouldn't have. But what we're learning here is going to be exactly the same process as what we'll be doing with that t-test. Our theme this week is movies. And for this z-test, we're going to learn about movie ticket costs between two different movie theaters. And here is our setup. An investor is interested in the prices of movie tickets between the single-screen Aztec Theater and the larger Springfield Googleplex theaters. From past earning reports, he calculates the standard deviation for each theater. He then selects an independent random sample of ticket prices from each theater. So in this case, we know something about the population. We know the standard deviation, and we know that because of these past earning reports. Now we can do a z-test. So let's walk through the 5 steps of hypothesis testing. Step number 1 is we look at our data and determine what kind of test can we do. We select the appropriate statistic. So let's see what we know. We have 2 samples, each drawn from a population. The first sample is size 345, the second is 350. So these are fairly large samples. We have a sample mean for each of these 2 samples. The first sample mean is $9.11. The second, $9.16. The population standard deviation from Aztec Theater is 1.9. From the Googleplex, it is 1.7. Those are the values that are going to stand in for the population standard deviation. I've selected 2 samples from 2 populations. Population 1 would be all the tickets sold at the Aztec Theater, and population 2 would be all the tickets sold at the Googleplex Theater. And now I have 2 samples drawn from those 2 populations, a subset of 345 and 350 ticket prices from each of those 2 populations. I'm going to start with the assumption that those 2 ticket prices are the same, that these 2 theaters charge on average the same amount for a ticket. And then we're going to test that to see if the evidence would support that. We have 2 samples. 2 groups. They're categorical. Those 2 groups, Aztec Theater, Googleplex Theater. And we're measuring something, the dependent variable, that has a mean. It's ticket prices, number of dollars, the cost for a ticket. And because we have some additional information, the population standard deviation, we can now do our 2-sample z-test. What are the assumptions that we want to look for, that we want to test for to make sure are true before we can do this test? The first assumption will be that of outliers. We don't want to have any extreme data or extreme outliers that would distort our findings. The chance of this, pretty low. If the average ticket prices are around $10, it's highly unlikely we're going to have anybody who's paying $100 or $1,000 for a ticket. That would be an outlier. It's probably very unlikely to occur. Also, we're probably not going to have any missing data. As we're pulling this information, we're only pulling complete cases. So for the most part, we can be confident that we have a complete data set. We would definitely want to check for missing data as well. The assumption of independence means that the scores in one sample don't influence the other. That means that the management at the Aztec Theater is setting their ticket prices independently of what's going on across town at the Googleplex Theater. Has that assumption been met? Well, we'd want to look into that a little more just to make sure that was the case. We're going to assume that it is for this example. But if there was some kind of relationship between how those prices were being set, then this wouldn't be the test that we could use. So we'll assume that the management in both places is just setting those ticket prices, and they're not doing it based on what the other theater is doing, which would be non-independence. Then the last assumption we're going to look for is normality, the sampling distribution being normally distributed. What I could do to make sure that this assumption has been met is I could do a normality test for each sample. What that's going to tell me is whether there's a normal distribution of the sample data. And if the sample data, dependent variable, the costs, is normally distributed, then I can assume it's being drawn from a normally distributed population. But that is not the assumption of normality. The assumption of normality is that each of these samples is drawn from a population that has a distribution of sample means that is normally distributed. Well, how do you test that? We take a shortcut. When we have really large sample sizes, if they're greater than size of 30 cases, then the central limit theorem kicks in. We can assume that the assumption of normality has been met. Step 2 is we're going to establish a null and alternative hypothesis. The null hypothesis is that both of these samples are drawn from populations that have equal means, or that mu1 equals mu2. Therefore, if I'm writing out my null hypothesis, I would write it as h sub 0 colon mu1 equals mu2. Although, I could write this slightly differently. If mu1 and mu2 are equal, and I subtract one from the other, the difference between them should be 0. So if I have two things that are the same, the difference is 0. I could write it that way. And I want to point that out because we're going to see that coming up again when we look at our spreadsheet. The alternative hypothesis would be h sub 1 colon mu1 does not equal mu2. The first sample is drawn from a population that has a mean that is different than the population from which the second sample was drawn. Once I've established my null and alternative hypothesis, then step 3, we're going to select the criterion for statistical significance. We'll need to have some kind of alpha level. We're going to keep our alpha level at 0.05, unless we're told otherwise, usually in a word problem. The critical value for any normal distribution based upon an alpha of 0.05 is always going to be the same. So this is another good reason to do both that probability test and the z-test together. The critical value is really easy to calculate. Next week, when we learn about t-tests, we'll see that we have to adjust our critical value by the sample size, or the degrees of freedom. In this case, none of that matters. We will always use the same critical value. When you have an alpha of 0.05, two-tailed test, the critical value for that normal distribution is always going to be positive or negative 1.96. That really means 1.96 standard deviations. And the positive negative means that if we go past positive 1.96 or we go past negative 1.96, either direction would be over the fence. The critical value sets the fence. We're looking for a test statistic that exceeds that critical value. If the test statistic exceeds the critical value, it is statistically significantly different. That's when we would reject the null hypothesis. If we are doing a one-tailed test at alpha of 0.05, the critical value is always going to be positive 1.645 if we're doing a right-tailed test. And if we're doing a left-tailed test, it will be negative 1.645. The key thing to remember is if you do a one-tailed test, the direction of change has to match what you predicted. If you're looking for changes greater than, and instead you find a value that's statistically significantly less than, it's still not significant. The direction of change has to be the direction that you predicted. Step 4, we're going to calculate the test statistic. And here's the formula that we could use to do that. What do we have here? We have some means. We're looking for a mean difference. We have the standard deviations of the population. That's where those are going to plug in. We have our two sample sizes. And we also have this thing, this d sub 0. Well, what is that? Well, the d sub 0 is actually the difference between the population means. Now, at this point, you might get a little worried because we don't know the population means. We're going to use the sample means and make a good guess at what the population means would be. So how am I going to do this test? How am I going to get the difference of the population means if I don't know the population means? Well, the way that we're going to solve for that is, remember our null hypothesis, which is that mu1 equals mu2. So what are we saying that we assume is the difference of the population means? 0. So when you look at that numerator, we have the difference between the sample means minus the difference between the population mean. But that population mean difference we assume is going to be 0. Now, one reason why I mention that is we can do a hypothesis test where we ask whether the mean difference is greater than 5, or plug in some other value as a hypothesized mean difference. Most of the time, however, we're going to be using a mean difference of 0 that we assume will be the case in the population. We're going to use Excel for doing the calculations in this case. And so I'd like you to go to the spreadsheet. We're going to start on the To Sample Z tab. And the first thing you'll notice is we need some data. The data are always going to be found on the last tab, the one that says Data. Go to the Data tab on the far right at the bottom of your screen, and let's get the data for the Aztec and the Googleplex theaters. Select both columns. Right-click and copy. Before we click off of this, note these settings for our two sample z-test, the alpha and those two standard deviations. We'll need those in a moment. Now click on the To Sample Z tab and paste the data that we've just copied from the Data tab. In order for the spreadsheet to work, we need to have some settings. These are the settings that are still on the Data tab, but I'll remind you of what they are so we can fill them in. The first is the alpha level. That's going to be easy. It's a 0.05. So you see where it asks for the alpha level, plug in 0.05. The hypothesized mean difference, or d sub 0, that should be a value of 0. Now, that's already entered for you by default, but this is where we could adjust this setting for a difference of 5 or some other hypothesized value. So what we need now are the standard deviations of the populations. For the first set of data for the Aztec Theater, plug in a 1.9. And for the second, for the Googleplex, plug in a 1.7. And now we see the results from our test. So let's see what we have here. Our settings are here at the top. Because we have an alpha level of 0.05, our confidence coefficient is 95%. If you are using, let's say, a 90% confidence interval, be sure that you change the alpha level, not the confidence coefficient directly. When you change the alpha to a 0.1 or 0.01, then your confidence coefficient will change as it should. We have the sample size, the sample mean, the standard error. Those are all calculated directly from the data that you've copied into this spreadsheet, as well as the margin of error, the pooled estimate of the mean difference, and the pooled variance. I'm going to tell you more about pooled variance when we talk about the independent sample t-test. The criteria, we have a critical value for a two-tailed test set at 1.96. That will always be the case. Anytime we do an alpha of 0.05 using a normal distribution, the critical value will always be 1.96. And remember, it could be either positive or negative. We also have the 95% confidence interval. There's the lower limit and the upper limit. We'll come back to those. In the test results, we see the test statistic. It's a negative 0.36. Cohen's d is our effect size. And we have the p-value for the two-tailed test at 0.717. We have some findings, but we're going to need to interpret those findings. Remember, there are three ways of determining statistical significance. All of these are going to tell us the same story. So first of all, let's take a look at the critical value. It's a 1.96. However, our test statistic is a negative 0.36. Now that 1.96 go either direction. If we're looking for a negative 1.9 and we only make it to 0.3, we did not make it over the fence. Not significant. Second, we can look at the p-value. The p-value for this test was a 0.72. If you convert that to dollars and cents, it's like 72 cents. That is not even close to a nickel. It's way over. It's much larger than 0.05. So it's not the less than 0.05 that we were looking for. The third thing I can look for is my confidence interval. It's a negative 0.318 to positive 2.19. And you'll notice that that includes 0. Do you remember our hypothesized mean difference? It's 0. If my confidence interval includes 0, or my hypothesized mean difference, then that null hypothesis value could be readily within the findings that I would get for repeated samples. All of these tell me the same thing. No statistically significant difference. It's non-significant. I will fail to reject the null hypothesis. Now that I've done my statistical test, I need to write it up in APA style. It'd look like this. A study was conducted to determine whether the cost of movie tickets were statistically significantly different between the Aztec Theater and the Springfield Googleplex Theater. Because the standard deviation from both populations was known, a two-sample z-test was used. The cost of movie tickets at the Aztec Theater was not statistically significantly different than the cost at the Googleplex Theater. I've included my z-value, the p-value, the confidence interval, and the effect size, which in this case is a 0.03, which is very, very small. There was really no meaningful difference between the costs of the tickets at one theater chain versus the other. Sometimes we have to do a test where we don't have any data. In those cases, I have another part of this spreadsheet that you can use. It says two-sample z-test without data. If you have information to plug in, you can actually do this test without having any raw data at all. So here's how this would work. Look at our settings. We see sample size, sample mean, population, standard deviation, and alpha. Let's plug in this information. So for sample size, we have 40 and 50. For our sample means, 25.6 and 22.8. Standard deviations are 5.3 and 6. And for our alpha level, let's use 0.05. Now you can see the findings. So we have our test results. Here in the lower box, our critical value, the test value, the p-value, whether or not it is significant, plus our confidence interval here on the right lower area. That is how we can do a hypothesis test with two sample means. But sometimes we don't have means, we have counts. And those counts allow us to create proportions. So we need another type of test where we can see whether there's a statistically significant difference between two sample proportions. And for that, we're going to use the two sample proportion test. The setup is going to be very similar to what we've done with our z-test. In fact, the statistic that we'll be calculating will also be a z-statistic, even though we're using proportions. A two-sample proportion test is a parametric procedure. What does that mean? I have two samples drawn from populations. The sample proportion is a statistic. The population proportion is a parameter. So I am using sample proportions to estimate population proportions. That's why this is a parametric test. It's testing whether one sample proportion is statistically significantly different than another sample proportion. I have one sample drawn from population A, a second sample drawn from population B. My starting point, my assumption is going to be that both of these samples have been drawn from populations that have equal proportions, or proportion 1 equals proportion 2. Sticking with our idea of movies as the theme for this week, we're going to answer a different question. You know, sometimes movies are based on books. And if you've read the book, you might feel like the movie was a little disappointing because you had images of how it was supposed to be in your mind for having read the book. And then maybe if you didn't read the book, you might actually enjoy the movie more. So we're going to do a proportion test based on that idea. Is the book better than the movie? A recent top grossing movie was based on a best-selling book. 500 movie patrons were surveyed upon leaving the theater. They were asked two questions. A, whether they had read the book before seeing the movie, and B, whether they would give the movie version a rating of fresh or rotten. If you're not familiar with the Rotten Tomatoes website, fresh means that they liked it, and rotten means that they didn't like it. What we have here are counts. We have categories. People either read the book or they didn't, and they either liked the movie or they didn't. And we want to know whether those proportions are the same based on whether they read the book or they did not. We have 196 patrons who read the book. They are representative of the population of all people who read the book. 116 of them rated the movie fresh. Now, we need a proportion. So what we're going to do is divide the smaller number by the larger number, or 116 divided by 196, a proportion is 0.59. Remember that proportions and percentages are functionally the same. This would be the same as 59%. The second population is those who did not read the book. We got a sample of 304 of those patrons who did not read the book. 206 of them rated the movie fresh. 206 divided by 304 gives us a proportion of 0.68, or 68%. 68% is different than 59%, but is it statistically significantly different? To answer that question, we're going to need to use a proportion test. We have two samples, each drawn from a population. The populations are those who read the book, those who did not read the book. Our assumption is going to be that the rate or the percentage of those who liked the movie would be the same regardless of whether they've read the book. So we're going to use that in our null hypothesis. We are using a dependent variable of counts. This is how many people liked the movie. An independent variable with two levels, two different populations, and a dependent variable based on counts gives us the setup for doing a two-sample proportion test. All tests are built upon assumptions. The first assumption is no outliers. Well, this one's going to be really easy. Because remember that the question was, did you read the book or not? Yes or no, 1 or 0. And did you like the movie or not? 1 or 0. There's really no way of having outliers in that setup. So if we look at our data set and something is coded as an 11, we're probably going to think that was supposed to be a 1, and we'll just change that number. But there's no outliers because there's only 2 options for our answers. Missing data is probably also not going to be an issue. If someone didn't answer the question of whether they'd read the book or didn't tell us whether they liked the movie, we're simply not going to include them in the data set. Independence could be an issue if we have groups of people, friends who have gone to see the movie together, and they're all raving about how good the movie was, or they were all disappointed. If you were one of those people, you might be influenced by what your friend thought about the movie. So independence is the assumption that each answer is not influenced by others in the sample. We would have to structure our data collection in a way to make sure that the answers are not being influenced. That would meet our assumption for independence. We're going to be using a normal distribution for this proportion test. And I said that I chose the proportion test and the z-test because they both rely on the normal distribution. And that's true. However, there is one assumption that we must check if we're going to use a normal distribution with our proportions test. We need to have a large enough sample size. And here's how we're going to check for this assumption. We can use a normal distribution if this criteria has been met. N times p is greater than 5, and n times 1 minus p is greater than 5. To help this make sense, I've included the proportions and the sample sizes in this example. So let's check sample number 1. 1.96 times 0.59 is 116. That is greater than 5. So this part of the assumption has been met. 196 times 1 minus 0.59 is 80, also greater than 5. So the assumption has been met for this first sample. But you have to check the assumption for both samples, and both samples have to pass. If one passes and the other one doesn't, you still can't use this, or we would need to use a corrective factor. Let's check that second sample. 304 times 0.68 is 207. That's greater than 5. And 304 times 1 minus 0.68 is 98, also greater than 5. The assumption has been met. We can use the normal distribution for this test. And that brings us to step number 2. Let's establish the null and the alternative hypothesis. The null hypothesis will be that both samples are drawn from populations whose proportions are equal. I will write my null hypothesis as H sub 0. The population proportion 1 is equal to population proportion 2, which also would mean that if I were to subtract those two population proportions, their difference would be 0. There are other ways that we could write this null hypothesis. Specifically, we could use a lowercase p and an uppercase p. Now, the way that I like to do this is I like to use Greek letters for population parameters and English letters for sample statistics. So I am using pi to stand in for the population parameter. You'll notice that our textbook uses a capital P, and that's fine too. So capital P, lowercase p, or pi versus lowercase p, exactly the same idea here. This sample is drawn from a population whose proportion is the same as the population from which the second sample is drawn. That means our alternative hypothesis will be population proportion 1 does not equal population proportion 2. For step 3, we're going to calculate the criterion for statistical significance. We're going to keep our alpha level at 0.05. And that means our critical value, as it is for all normal distribution tests, is going to be 1.96 for that alpha 0.05 two-tailed test. If we were doing a one-tailed test at an alpha level of 0.05, the critical value would either be positive 1.645 or negative 1.645. But you can assume that we're going to be doing an alpha of 0.05 two-tailed test unless you're told somewhere in the word problem that we'll be using some other setting. Step 4 is to calculate the test statistic. So you'll notice this is also a z-test, and z equals the difference between the sample proportions times this information down here, which uses proportions and sample sizes. And of course, we're not going to calculate that. We're going to let our spreadsheet do that mathematical work for us. And we'll be on the 2-prop test tab for this example. You can see that we need some data, and those data are going to be included on the Data tab. So let's go to the Data tab, grab the 2 columns, read the book, and no read. So columns L and M in this case. Select both of those columns. Right-click and copy. You'll notice there are some additional settings. We'll need those in a moment, and I'll remind you of what those are. Click back to the 2-prop test tab and paste in this data. Now we need a response of interest. What this means is we have to take one of the examples of the response options and plug that in as the response we're looking for. You need to make sure that what you enter as your response of interest is spelled exactly the same way as it is in the data set. So for instance, capital F fresh, that could be our response of interest for both the read the book and didn't read the book populations. When you're doing your data cleaning, if you have, let's say, lowercase f fresh as one of the response options, that is a different response than the capitalized version. In other words, you need to check your data set to make sure that all the response options are spelled the same way. And if so, then you could use the spreadsheet to account for that. We have our alpha level set at 0.05, and we can check the assumptions. We can see that both of the samples have passed the assumptions check. That means that we can use a normal distribution. Among our sample data, we find our sample size, the counts for the responses, the proportions based on those counts, as well as things like the pooled estimate of the proportion, the standard error, margin of error, and the point estimate of the difference. Under our criteria, you'll see we have critical values for both 1- and 2-tailed tests, as well as the confidence interval, upper and lower limit. And then here at the bottom, we see the test results. Here's our test statistic, our Cohen's H effect size, and the p-value for this 2-tailed test. There's a lot of information here. We're going to need to, step 5, interpret the results and write up the findings. Let's start with our interpretation. The first criteria that we could use for interpretation is whether our test statistic exceeds our critical value. Our test statistic is a negative 1.956, but we needed to get to a negative 1.96. You can see it didn't quite make it over the fence. When we look at our p-value, we need something less than or equal to 0.05, and we have a p-value of 0.051, which means that it is still greater than 0.05. We were looking for a hypothesized difference of 0, and I can see that this negative 0.17 is negative, whereas this 0.002 is positive. That means it crosses 0. 0 is included in the confidence interval. All of this tells me the same thing. This test is non-significant. We did not reach the level of significance. Almost, but not quite. So I think that's something we need to talk a little bit more about. But first, let's finish our write-up. In APA style, we would say a 2-sample proportion test was used to determine whether the patrons who read the book upon which a movie was based gave higher or lower ratings to the movie. Although the proportion of patrons who read the book and rated the movie fresh, 59%, was lower than the fresh ratings from patrons who did not read the book, 68%, the difference was not statistically significant. Our Z, P of 0.051, confidence interval, and our effect size. There is not sufficient evidence to conclude that book readers have higher expectations for the movie. Not every time that we do one of these proportions tests are we going to have the data. So let's scroll down a little bit in this spreadsheet and let's find the two-sample proportion test without data. In this example, we have 200 items with a proportion of 0.44 and a second independent sample of 250 items with a proportion of 0.31. We'll keep our alpha level at 0.01. So let's plug in. Group 1 is going to be 200. Group 2 is 250. Let's set our alpha level to 0.01. And at this point, we need to get the sample size, which we don't have. So let me show you two ways that we could get this sample size value. The first is I could use math. I could use the formula in the Excel spreadsheet. So here's equal sign the group size times 0.31, which comes from our word problem. And then that will give us a sample proportion. The second is you could just skip that altogether and you could directly enter these proportions. If you simply typed 0.31, 0.44 in that second sample proportion, that would work as well. However, if you do that, remember you'll break the spreadsheet, so you'd probably want to close without saving so that you wouldn't overwrite any of the content. However, you can plug in these numbers directly and still get the answers. In this case, with our alpha level at 0.01, our confidence interval set at 0.99, our test statistic should be 2.8418. The Cohen's H is 0.2695. P-value, 0.0045. And when we look at those numbers, is that statistically significant at 0.01? Also yes. Now, in our example, we had a p-value of 0.051, which is almost 0.05, but it's not over the fence. It was very close to being statistically significant, but was not significant. However, it probably bothers you. We were so close. How do we interpret that p-value? Now, I could explain it to you, but I did create a video that I think explains it even better because I used a historic example of the lady tasting tea and I updated it with our dogs. So we have the dogs tasting, well, it's supposed to look like tea, but instead it's beef bouillon. It's much better to watch that video to explain the two ways that we could approach significance testing. And it'll give you a little bit of history about statistics as well as an explanation of the two approaches. So there's some important things to consider as you watch this video. If you're designing a research project, you want to think about the power of your test as you're choosing a sample size. So for instance, you'll want to get a sample size that will be sufficient to find statistical significance based on an effect size that you've either calculated or you found from previous research. And this is also why you want to report an effect size for any research that you do. So as you watch that video, I think you're going to get some good ideas about the reasons why we're doing what we're doing. Well, that's all I have for this week. So I want to say thank you for being here, and I'll see you next week.